So the next speaker is Jaroslav Bendik, who is a researcher from Certora, and he's going to be talking about testing your code on arbitrary states, aka formal verification. Please give a warm welcome to Jaroslav. Thank you.
Thank you for the introduction. Can you hear me? You can hear me, right? I want to basically show you how you can use formal verification to improve the security of your code. I'm sure that you have heard about many bugs that have appeared. They might have appeared in small contracts. They might have appeared in big contracts. In many cases, they led to losing millions of US dollars. But it's not just about money. The contracts are losing trust of the community. Bugs are issues. And I think we all agree that we want to get rid of bugs. We want to prevent bugs from being exploited, from being even appeared in the smart contracts. And the question is how to achieve this. There are many techniques that are usually used, like testing, fuzzing, auditing. You know these techniques. These techniques are actually used also in other areas of software development process. So, like testing is used in almost every software company, right? But in this talk, we are not talking about these classical techniques. We are talking about formal verification. And formal verification might not be so well known, and it might not be so widely used. It is the case. But I hope that after this talk, you will see that it has some value and it can be beneficial to use it, especially in the area of DeFi. So what is formal verification? There are many definitions. This is one from Wikipedia. And it says that formal verification is the act of proving or disproving correctness of algorithms with respect to certain formal specification using some formal methods of mathematics. Important parts here are proving or disproving. This basically means that you should get some guarantee, mathematical guarantee that there are no bugs. But what does it mean, no bugs? This is the other part of the definition. Formal specification. You need to properly, without any ambiguity, define what are the properties that you want to verify. Then you verify it. So if you write wrong specification and you run some formal verification, it says there are no bugs. Might not be the case because you might have wrong specification. So you need to write specification and then you can apply the formal verification. And the specification is not written in English. It has to be precise. Okay? So there are many myths and claims about formal verification. Maybe we have heard about these. I don't know how much you know actually about formal verification. Some of these myths says that formal verification can be only used to prove things, or that the hardest problem is computational, meaning that formal verification does not scale for real programs, okay? Because you are really providing this guarantee that there are no bugs, like no execution can lead to a bug. Another claim, you get a bulletproof code if you run formal verification, or claims that formal verification can replace auditing or testing, or that you apply formal verification once, at the end you are done with the code and then you verify. So these are some claims, maybe myths, and during this talk I will try to shed some light on these and tell you what is the reality at the end of this talk. Good. There are many existing tools that are using some kind of formal methods. This slide is showing just some of them, and we can classify these into two groups. One can be called proof assistants, and basically these tools are, for instance, Isabel, Daphne, Coq, Cake. They can be used to prove very interesting properties of your program, but on the other hand, the user has to be very experienced. So you need to know how to use these tools. You basically go over your code. You are providing some lemmas about individual instructions, individual functions in the code, and then you can prove complicated stuff. But it takes a lot of time, okay? And if you change your code, you need to adjust the proof. So very powerful tools, but hard to use. On the other side, we have fuzzing and static analysis tools. So these tools are easier to use. They are running quite quickly. The user does not need to really know how these tools works. And if you change your code, you can just run the tool again, and it gives you some quick answer. But these tools are limited in some sense. They can give you some false positive or false negative answers, meaning like they tell you there is a bug, but it might not be a real bug, or they might miss a bug. They are not exhaustive, okay? And at our company, we are developing something called Certora Prover. We are trying to be somewhere in between. So basically, our tool should give you the guarantee that there is no bug. But the hard part is that the user does not need to know formal verification, but the user needs to write the specification. So you really need to understand the underlying contract, and you need to properly specify all the behavior and all the possible bugs that might happen. You don't need to say like, Alex is stealing 1,000 Ethereums, okay? But you specify some properties. I will show you some examples later. So in the rest of the talk, I will illustrate how formal verification can be implemented following the example of Certora Prover. The input of our tool is your program and some specification. And the output is either execution of the program that violates the specification, or you get some mathematical guarantee that there's no violation. And since this problem of formal verification is quite hard, we are really checking every possible execution of the program. Then sometimes we time out. This problem is really hard. But we are trying to find the bugs or give you the proofs, but sometimes we time out. It can happen. So two things to explain now. How to write the specification and how does the tool work. So let me start with the specification. This is a simple Solidity smart contract example. There's a bug in this example. So let me just briefly explain this, this code. We have some mapping called balances. So this is basically like storing the information about balance of individual users of the smart contract. And then we have these two functions. Transfer takes some address from and some address to and some amount, and it should transfer the amount. And then we have another function, balances of, which just takes some address and tells you the balance on that address. And now the question is, what is wrong about this function transfer? So let's just explain how it works. We require that the from account has at least amount, which makes sense if you want to transfer that amount. And then you compute the new balance from, the new balance to, store it to some variables, then you update the balances using these two variables. So what is wrong? Can we see some bug in this function? What can go wrong? Right. So this is actually a bug that appeared already several times. And I'm showing this one because one of our customers just introduced this bug in their, like it was not in production, it was during the development. This customer is using our tool, so they're writing some specification and running tests during CI, okay? So we have a rule that can catch this bug. That's why I'm talking about this one. And yeah, the bug is that if you send money to yourself, you can increase your balance. And yeah, it's because you first compute the new balance, like you're adding the amount, and then you decrease your balance, but then you override it again. So I hope you can see this behavior, okay? And now the question is, how can you find this bug using our tool? So as I said, you need to write the specification. And this specification might not be saying that when you send some money to yourself, you will increase your balance. It might be saying something else, but it should reveal this bug, okay? So here's the rule that was used in the CI tests. What is a rule? So our specification consists of several rules. Every rule is like a single piece of specification we want to verify with our tool, okay? This rule is called sum of, from, and to balances stay the same. So basically it is saying that if you execute the transfer function, then the sum of balances before the execution and after the execution is the same. So no tokens can appear basically, or disappear. How does it work? You say that you have some address to, and you have some amount. We are not saying what is amount, we are not saying what is the address, just that we have some address and some amount. Then you say that you have some environment E. What does it mean? This basically represents the Solidity global variables like message sender, message value, block timestamp, okay? So we are basically saying we are at some state of the smart contract, we have some amount, we have some address too. Then we compute the sum of balances of message sender and to, okay, by calling the Solidity functions. And then we call the transfer. So we are transferring amount from message sender to, and then we check that the new sum of these two balances is the same as before the transfer. And our tool is basically checking if there is like any assignment to amount E that violates this assertion. Okay? And there is one. In this case, not just one, there are many. Okay? And Alice is one of these examples because the initial sum of Alice is 14, like 7 plus 7, and then after the transfer, it becomes 24. So this rule will be violated, and it can get you to understanding this counterexample. Okay, let me show you another example. So this is some like a generic boilerplate how to write specification in our specification language. So typically it goes like this. You say that you are at some state of the contract, so you have some like message sender, message value. You have some storage state. You do not say what is the current state of the storage. Then you can have some requirements, some assumptions about the message sender, for instance, or about the storage. So you might, for instance, require that there are at least 10 accounts in your smart contract, okay? And that the sum of balances is lower than 100. You can have some assumptions. Then you invoke some function from Solidity, and this function might return some value, some x, for instance. Then you can have some requirements, some assumptions about the result of this execution, like assumptions about x or assumptions about the storage that was changed because of the invocation of the function. Then you can call another function, for instance. Maybe using the same E variable, maybe you can define new E variable. So you have like two people that are calling the smart contract and they are somehow interacting. And then again, you can require something about the execution of that function. And at the end, you have one assertion, or maybe more assertions, that are talking about the effects of the execution of the function. Like in case of Alice, okay, the sum has not changed. So you can have like arbitrary logical reasoning about the effects of the invocations of the functions. And yes, as I said before, our tool checks this for arbitrary value of E, arbitrary values of, state of the smart contract, but we follow the requirements that you provide. And this is not everything. Our verification language can allow you to do more crazy stuff. So you can define some hooks and goes. These are basically, you can modify the underlying Solidity code. So whenever you invoke some function, you can count invocations of functions, or you can summarize some functions, meaning you can override some functions in Solidity, which might be very useful. For instance, if you are verifying some property that does not depend on some function, you just override the function. You just say, this is something simple, I don't care what this function does, okay? You can use quantifiers, like for every Alice, there is some John that does something. If Alice, or I don't know, you can have muffins, meaning we are not limited to using 256, you can have arbitrary numbers, and many other features. And actually tonight we have a session of Tomer Ganor from Certora. He will show you more. So this is all about specification from my side today. I will be happy to answer some questions or talk later. But now let's see how the tool actually works. So this picture summarizes the steps that we do during the verification. And I will now go individually over these steps and just tell you briefly something about them. The first step is that we take the Solidity and we compile it to EVM bytecode. And the reason is that different compilers produce different bytecodes. They might behave differently with respect to the specification. And sometimes the compilers even contain some bugs. And we've actually identified some bugs that are fixed also because of us. We are very proud of this. But the important information is that we need to verify the bytecode that is uploaded to the blockchain to make sure that, the bytecode that is used by our customer. And I might be saying like, this is something not nice. It's not nice, so there is some drawback. And the drawback is that if we find a violation of the specification, we need to show to the user what is the violation, like what is the execution of the smart contract. So we need to map it back from the bytecode to the Solidity, and this might be hard. Another issue is that the bytecode is complicated, it's not easy to read. It is using so many basic instructions, and this code is really hard to automatically analyze. And we are trying to automatically analyze the program. So even bytecode is not good for us. And hence, in the next step, we take this bytecode and we convert it to our custom program representation. And we call this one a 3 address code. I'm not sure, maybe you have heard about some 3 address codes before. Yeah, these are custom one. And basically, the 3 address code is using only a small number of unique instructions. And it's quite simple, which means that it's easy to analyze. And also, if you can translate another language, like Solana, maybe, to our 3 address code, you can run our tool on it. So there are other advantages of this. Good. Other part of the input is the specification. So basically, we also take the specification and we somehow merge it with the bytecode and form together the 3 address code, the program representation. And we take the assertions from the specification, put these as assertions to the tag program, and then actually it's about trying to reach and violate an assertion in the tag program. This is the verification task now. Okay, what is the next step? We have this tag program that represents the input basically, and now we try to analyze it and simplify it using some static analysis. So the goal is, identify useful information. So for instance, we run some pointer analysis. For example, if you have some 2 functions, in some cases we can identify that these 2 functions do not touch the same memory. So they do not interact with each other, and this can really simplify the verification process because you know that there is no interaction between these 2 functions. Or we do program slicing. I'll actually explain this on an example soon. We also do some value range analysis, meaning that you can have uint 256 variable, meaning so many possible values, but perhaps this variable is actually bounded in your program. It's always between 0 and 10. And if you get this information, the verification is much easier because you don't need to assume so many combinations of values of variables. So we reveal very important information about the program. And we also try to simplify it. We change it so that it is like in a suitable shape for the following pipeline. Now the slicing example. I don't know if you know what is program slicing. So very small example. You have a program with 2 structures, x and y. Both have internal variable f. xf is 1, yf is 2. Then we change the value of yf to 3. And then we have this assertion that xf is 1. Now, let's say that this is the specification, okay? The assertion is the specification. And you can see that this holds. I mean, it's a trivial program. But the program slicing. The program slicing is about observing that the value of y does not matter. It does not affect the assertion. So you can basically remove this part from the program, and you can work just with this program. It's equivalent program with respect to the specification. So we are trying to do automatically these simplifications of the program before we continue with the following pipeline. Okay, good. Next step. So we have this 3 address code. It's a program. It's really nice. It's simple. And now we generate something that we call verification condition. So what is verification condition? It's a logical formula. You can imagine like a mathematical formula, some equations over some variables. And this formula is satisfiable if and only if you can violate its specification. And also the variables from this formula, they somehow correspond to variables from the solidity. And so if you get a satisfying assignment of that formula, you actually get execution of the smart contract that shows you the valuation. I'll show you an example later. But the question is, okay, how do we build this formula? Let me state it in English. So the formula says that there exist initial values of variables of the program, such that after execution of that program with those variables, with those values, you evaluate the assertion. Okay? If this formula is true, then you have the execution that violates the specification. We are done. Right. But this is English. We need to use some logic here. The important property, as I have said, you need to ensure this mapping back to solidity. So the variables that will appear in the formula really have to correspond to variables from the program, and you also need to somehow encode the execution, like which branches were taken in the program, which functions were called. You need to encode all of these. So how do you turn the program into a logical formula? That's the question. The answer is, we don't have so much time, so the answer is very simple. And that's because the 3-address code is almost a formula. So let me explain. 3-address code means that you are using only 3 instructions per, 3 addresses per instruction. So they are very simple. Okay. Second thing, it's in a so-called static single assignment form. This means that you cannot change values of variables in your program. But you want to do that, right? So if you want to increase x by 5, you create a new variable, x1, and you say that x1 is x plus 5. And yeah, this now looks like a logical formula, like a mathematical formula, because you are not changing values of variables. They have like a unique value, not unique, like given value. You can express the value of variable in different ways, but it's like one value. So assignments in the program looks like logical formulas, right? What else do we have? Several other instructions, for instance, branching. So you have some condition. If C, then do branch A, else do branch B. These are implications, logical implications. If the condition holds, then you perform A. What is A? Maybe some assignments, logical formulas, right? So this works. And yeah, then we also need to deal with loops and some assumptions, some assertions. I will not cover these, but basically you can convert all the instructions from 3-address code to logical formulas and somehow compose them. And then you form the sentence from the previous slide and you check it. So that's the idea. Okay, what is the next step? In the next step, we take this verification condition and we convert it to something called SMT. So SMT stands for Satisfiability Modulo Theory. And the theory might be integers, reals, it might be using nonlinear operations, linear operations. So basically, and then there are tools, there are solvers that are solving like these problems expressed in SMT. Now what's the difference between verification condition and SMT? In the verification condition, we do not say how we represent the numbers. If we use bit vectors or if we use integers. And yeah, in the SMT we do. And there are many solvers. We are trying to somehow combine them, communicate with them, run these solvers in parallel. So this is basically about maybe verification condition is algorithm. SMT solving might be program that solves your verification condition. It's not that easy. Many people work on this at our company, but I will not go into details about the SMT solving. It's a different chapter. Okay, so we are getting to the end of the pipeline. You successfully run the verification and you either have a proof or you have a bug. Okay, are we done? No, we are not done, definitely not done. So what happens if you find a counterexample? This is an example of a report that our tool is providing. So let me explain. This is a report from the Alice example, like the transfer where you can send money to yourself, okay? On the left-hand side, you will see all the rules that you have verified. In this case, we are just dealing with one rule. On the right-hand side, we can show the values of variables from the specification. So remember, in the rule, you just define some variables, but then the tool is trying to find some values of these variables that would evaluate the assertion, okay? So here you can see the message sender, you can see the two, they are the same, it's some Alice. And you are sending 5, amount was 5. And the sum was 14, meaning that Alice's balance was 7 at the start of the computation, okay? So this helps you understand a bit what was happening. And then we have this call trace. So basically in the call trace, we first tell you what was the initial value of the storage, what was the message sender, and so on. And then we perform the actions from the specification, from the solidity, and then we have the assertion. So what can you see here? The storage. So initially we had just one user in the account, and it was just this Alice. Her balance was 7. And then if we zoom a bit, you can, for instance, see what was happening during transfer with the balances mapping. So we have loaded 3 times 7. Then we have stored 2 because we have, removed the amount 5. And then we have stored 12. which was the wrong result, right? This was violating the specification, and this is how Alice got from 7 to 12 by just invoking the transfer function. This helps you to understand the counterexample. So are we done? Do you understand the counterexample? In this case, yes. In general, no. And in practice, the issue is that you might get the counterexample that is not real. And I have said that this should not be happening with formal verification. It might, if your specification is wrong, because you need to specify what is the state of your contract. So for instance, if you have a rule saying that the sum of balances never drops to 0, but you do not say that it's not initially at 0, then you can trivially violate the specification. So you need to specify correctly. Okay, good. So we are closing the myths now. Formal verification is used for proving things. It can be used to prove things, but it's also very good at finding bugs, violations. Second myth, the biggest problem is to compute it. Sometimes we time out, but the biggest problem is to write the specification. This is really hard, maybe easier than formal verification, but it takes some effort. Formal verification produces bulletproof code. No, you need to write the right specification. Okay, it's all about the specification. Formal verification replaces auditing. It does not, it's something else. Formal verification should be done just once at the end? No way. You should write the specification at the start, as we have heard at the previous talk. And then you should integrate formal verification in your CI and write it with every change of your code. Because you have the specification and then it's fully automated. Once you have the specification, you can just run it repeatedly. Okay, so what is better? Auditing, formal verification? No one. Just use both. Okay, and this is my almost closing slide. We hope that the community will start using our tool. Actually, the community is already using our tool. We are organizing several competitions where you can actually join us. You can start writing the specification. We can give you some money if you write some specification that catches some bugs. These might be real bugs, might be injected bugs. There's a way how you can start using our tool, how you can learn the specification. And for instance, it can also help you to deal with this catch the flag that we have just started today. You can use Certora Prover to solve these challenges. And finally, it's not just about competitions. Actually, we have this something called pay as you go, but it's like a trial version. You can start using our tool without paying any money. Just use it, try to find some valuations. This is a QR code. Please try it. And if you have any questions, reach me out. I'll be happy to talk. Thank you.
Thank you, Jaroslav. That was some fantastic insights into formal verification. So we've run out of time for this session, but Jaroslav from Certora is going to be around for the whole weekend, DSS. So if you have any questions, I'm sure you have a lot of questions on formal verification, so please reach out to Jaroslav. He'll be around. So thank you.